When we're calculating the pH of a solution, the first thing that we have to ask ourselves is, are we looking at a strong acid or base, or are we looking at a weak acid or base? And there's a couple ways to tell. One, you need to have a few of those strong acids memorized. Two, if it has hydroxide on it, then it's definitely a strong base. Three, if there is no K value mentioned in the question, it's probably a strong substance. So notice in this question, they do not give you a Ka of nitric acid. And that should be a reminder to you that that means that you don't need a Ka to solve for it. So when nitric acid is dissolving in water, it dissociates completely into H and NO3. And the molarity of hydrogen is how we determine pH. So we just need to figure out, based on this information and this information, what's going to be the molarity of our hydronium. In order to convert to molarity, we of course need to convert grams to moles. So we're going to have this many moles of the acid, and then we also need to put this in terms of liters. So we're going to use 0.850 instead. And then a simple matter of moles divided by liters will get us molarity, which is 0.0280. pH is negative log the molarity of hydronium, which we can assume that if we know the molarity of nitric acid, we know the molarity of hydronium because it 100% turns into hydronium. So we're going to do 0.0280, and our pH is 0.028, 1.55, which makes sense. This is a strong acid, it's relatively concentrated, so our pH is really low. Similar situation where we're now looking at a question asking for pH, and again they do not give you a Ka or a Kb, so that's an indicator that this is just a strong substance and you need to find molarity. In this case we see the hydroxide on NaOH, so we know that this is a strong base. We have a starting molarity here, but instead of this being a traditional moles per liter question, this is a dilution question. So we're going to be using M1V1 equals M2V2 because we need to figure out the pH after we have added water. So we started with 100 milliliters, 0.1 molar. We added 1500, so that means we're solving for M2, so we now have 1600 milliliters, which means M2 is 0.00625 molar. Okay, so this question is going to be just a teeny bit different because if we do traditional negative log 0.00625, we need to remember that we're solving for POH because when sodium hydroxide dissociates, it turns into sodium and hydroxide, not directly into hydrogen. 2.20, and then of course we have to remember pH plus pOH is always 14, so that means that our ultimate goal, which was to find pH, is to subtract the 2.2, and the pH of our solution would be 11.8, which again makes sense. We're looking at a strong base and that's a relatively high number. Now, when we're considering a question like this, we have a really clear indicator that we're looking at something different, which is that given Ka value. Also, HF, we can tell that it's an acid because it starts with hydrogen, but it is not one of the ones that we've memorized as strong, so another indicator that it's weak. That means that we need to consider the K value in terms of how much of it is actually turning into hydronium. So remember, water is a liquid, which means it does not affect equilibrium, but HF is aqueous. Okay, it will affect equilibrium. HF is going to be the denominator when we're setting up for Ka. So we know that Ka is supposed to equal the products divided by the reactants, which in this case is HF. Okay, we have a value for the Ka, and we also have a value for the HF. So what we need to realize is that as HF is reacting with water, it's turning into F and hydronium at the same rate. So when we're considering the change, we can set up an ice chart showing that we know we have an initial aqueous value for the molarity of HF when it's combined. We start with no ions of fluorine or hydronium. Okay, and then we have an unknown change, unknown change, unknown change, which means that at equilibrium, we know that that 1 molar HF will have gone down in a little bit, and the amount of F and H3O will have increased by that amount. To make our lives easier, we can assume that this X is very small. So probably when 1 molar minus X is calculated, it's just going to end up rounding to 1 molar. So we're going to make our lives easier by setting it up without that X first, and then we'll have to check and see if it was okay for us to make that assumption. So if we set up for K, we use the Ka of the acid, we use the molarity that basically didn't change, and we solve for our unknown values, which represent the molarity of hydronium and fluorine, but the fluorine really doesn't matter. If we're solving for pH, really this is the only one that matters. In order to make sure that this number is reliable, it needs to be less than 5% of the original molarity. So by comparing the new molarity to the old molarity, we see it's less than 5%, which means that we can go ahead and assume that this is the right answer. It's certainly going to be close enough. Which leads us to conclude that the pH of this solution would be 1.57. We'll just pause for 1 second in our quest for pH to talk about this concept because it's important. Obviously, if a Ka is larger or smaller, that's going to affect pH, but also the level of concentration of the substance will affect how much the substance is going to dissociate. So if we're looking at two different solutions of acetic acid, for example, one that is 1 molar and one that's only 0.1 molar, you would expect the 1 molar to have like a significantly larger pH, but what ends up happening is something kind of surprising. So keeping in mind that the molarity of the original substance is going to go at the bottom, and then the X values are going to be placed on top, we're going to assume that the molarities down here don't actually change by that much. So we'll just plug in the original molarities like this. So here's your concentrated solution, here's your dilute solution. The molarity of hydronium in the concentrated solution would be 0.0042, and the molarity in the dilute solution would be 0.0013. So yeah, it makes sense. There's more dissolved in the higher concentrated solution. But if you look in terms of percent, if we divide this by the original molarity, we have 0.42% dissociated. Whereas if we divide this one by the original molarity, which was much more dilute, and turn it into a percent, you end up with 1.3. So the takeaway from this is the less of a substance that is placed in the water, the more easily that substance dissociates. So the more dilute the solution, the higher the percent dissociation, which is not what that says. We're just gonna, percent. There we go. The higher the percent dissociation. This question brings us back to what we were doing. So in this case, we have a Kb, and that needs to tell you that this is going to be a base. So whether you recognize CH3NH2 as a base or not, just seeing this value right here lets you know that when it reacts with water, it takes a hydrogen and turns water into hydroxide. In terms of setup, we have the original substance at the bottom, we have the two ions being produced on top. So same thing. And we're going to go ahead and assume again that the 0.500 minus x that would normally go here, that x is small enough to disregard. So we're going to set it up like this, x squared over 0.5. When we solve for x, we do need to make sure that that's less than 5%. So we'll just divide that real quick, multiply by 100, which is about 3%. So, right under the wire. And very important, once again, to remember that this is a base. So when we plug in molarity, we're really plugging in the molarity of hydroxide. So that makes this the POH, not the pH directly. If we do 14 minus, then we will get the 12.17 that we're looking for. Last but not least, we can go backwards. If we're given pH, we are secretly being told what the molarity of X is. So even if you don't know the identity of the acid, you can use pH to kind of work backwards with a generic example. So we need to begin by doing 10 to the negative pH because that will give us the value for X working backwards. And remember that X is the conjugate base and the hydronium. So when we solve for Ka, we plug X in and square it by itself, and then divide by the original molarity to get this as the Ka of the acid, which we can then use to identify the acid from a chart. So if our acid is 3.5 times 10 to the negative 5, it is cyanic acid.